Right, good morning, AdMath students. This is the revision set of exercises from chapter 6. So this is number 1 on the revision exercise. And we start off with a semicircle with center O and also with radius 20 centimeters. They tell us DC is perpendicular to AB and C is the midpoint of OB. They want us firstly to go and find the angle DOC. Alright, so if we look at that triangle, that's at triangle DOC. Okay, if we look at that triangle, we can see that the length over here must be 20 because it's also a radius, and the OC length must be 10 because we were told that C is the midpoint of OB. Okay, that gives us a value to be able to find a ratio, and if we use the adjacent over the hypotenuse, which is what we've got here, we can say that the angle, and let's call it theta must be equal to the inverse cos of the 10 over 20, or a half. Okay, now remember we want to be working in radians, so let me just get my calculator here, and we're going to find a value in radians for that angle. Right, so a half and inverse cos gives us 1.0472. 1.0472. And of course we normally just need two significant figures or 3 if necessary, so 1.04 would be fine, or 1.05 would be fine for this. Now they want the area of the shaded region, so that is a sector. So what is the area of a sector? We have a formula for that. Area is a half r squared theta, and remember the theta has to be in radians if this formula works. So this is a half of 420 squared, and the theta, which we already worked out, so times 1,0472. Alright, so we can work that out, and we get an answer of 209.4. Okay, so the area is 209,4, and that would be centimeters squared for your units. Alright, so there we go, that's question number 1. Let's erase. And let's bring up question number 2. So I've got a couple of questions ready here for us. Let me just grab them. So here is question number 2. I'm just going to make it a little bit bigger. And we'll also erase this. Okay, so this question says that we have a circle and it has a center O, and it also has a radius of 10. So the AO line and the OB line will both be 10. The tangent to the circle at A meets OB and produces all the way out to to T. Given that the area of the triangle is 60, calculate the area of the sector. Alright, so the thing is, what we can already see from this diagram is this over here is a 90-degree triangle. Why? Because a radius and a tangent always makes a 90-degree triangle. This is something you may not yet know, but if you do know it, it's good, and you do need to know. It's one of the circle theorems, something we will look at in IG class still. Okay, so we also know that this is 10, but we know that the area is 60. So we could work out the AT length, because we know that if area is 60, it is half base times height, and the height we know is 10. So 10 times the base must be equal to the 60, and that tells us that 5, the base equals 60, because half of 10 is 5. The base must be equal to 12, so that means that the AT line is 12. Okay, so the AT line is 12. Alright. Now they want the area of the sector. Okay, so the first thing that we're going to need, if we need the area, is we're going to need an angle, and that's the angle over here. So that's the angle that we can work the sector out with. So we've now got two sides of the triangle. We've got the AT side and the AO side. So we know that that's 10 and 12, or 12 and 10 respectively, and that means we can use a ratio. So in that triangle, because it's 90 degrees, I can use AT as the side opposite the angle I'm looking for, and AO as the adjacent side. So that would be the tan ratio. So tan of the angle is 12 over 10, therefore the angle is the inverse tan of 12 over 10, and that comes out to 0.876. Right, and since it's 0.876, that is again a radian measure, and that means we can then calculate the area of the sector, because the sector will just be a half r squared theta. That's area of the sector, and we know the r is 10, so that's a half of 100 times the angle of 0.876. Sorry, there we go. And so 50 times that answer that we got previously is 43.80. So that's our area value, 43 comma 8 centimeters squared. Right, so there we go, that's number 2. We're also going to do number 3. Let me just quickly erase everything here again. Right, so let's bring out question number 3. And number 3 says the following. We have a circle with center O again, and we have a sector OAB. Sorry, the O is the center of the sector OAB, and CD is another arc. Okay, so there's two arcs in this one with center, the same center. Now the radius of OC, or the radius is R for that smaller one, but for DB we see that the line is 2. Now what is the area of ABCD? That's the little area over here, so let me shade that for you so you can see. They want to know this area of that little part of the shape. So clearly if we could find the area of the small sector and the area of the big sector and subtract them, we'd be left with that ABCD section that we have there. Okay. They do also tell us that if the area is 1/3 of the area of the sector OCD, okay, so in other words, that area that I've shaded is 1/3 the area of the small sector, then we've got to find the value of R. Alright, so clearly we're working with area of sectors. We only have one formula for that, so let's start with the formula and see how we can manipulate it. Okay, now we don't know the angle, but at this stage that doesn't really matter, okay, because we're going to work without knowing the value of the angle as such. Okay, so if it is a half r squared theta, and we know that in this case the OC is r, we can write that this is the area of OCD. Okay, so I'm just going to mark this here, OCD. Alright, so that is half r squared theta. Because we don't have any values, we've just labeled the angles as such and the radius as such. Now what would be the area of the bigger sector? Well, we know that that radius is r plus 2. So the area of OAB, and I'm going to write this over here. So this is area of OAB. Okay. And that will be equal to a half r plus 2 squared theta. okay, where theta is obviously the same as the theta in the other question. All right, and we could actually multiply that out and see what that gives us. So if I continue that over here, I'd get a half. Now r plus 2 squared is simply r squared plus 4r plus 4. Now remember, if you're not sure how to multiply out, this is a very important thing that you've been doing in IG work, is to be able to multiply two brackets of r plus 2 or two brackets of any binomial term, okay, and you always get that middle term, so check that you get that correctly. Okay, so there is the area expressions for the two sectors. Now we want the little area in between, okay, the ABCD. So that's obviously the big area minus the small area. So I'm going to write that ABCD. So let's make another statement here. So area of ABCD, that's my little shaded area, will be equal to a half r squared plus 2r plus 2. I just multiplied that half in, and then we must subtract a half, sorry, and all that is multiplied by theta. So let's put it in brackets, sorry, times theta minus the half r squared theta of the small sector. Okay, so if I multiply the theta into the brackets, and I'm going to just do that by removing the brackets here, and we know then that all of these will have theta with them. So the half r squared theta minus half r squared theta over here will disappear because we subtract, and we're left with just 2r theta plus 2 theta. So that is an expression for the area that we've already shaded. Alright, so we're going to need that in a moment. Okay, so I'm going to erase all of this here, because I don't think I'll need any more of this. And let's just erase here as well. Now they told us something about this shaded area. They said it was 1/3 the area of the sector. So we've got the area of the sector, that's here, the half r squared theta, and we've got the area of the shaded region, and we know that this area that I've just underlined is 1/3 the area of the half r squared theta. So what I'm going to do now is I'm going to write that 3 times, sorry, the 2r theta plus 2 theta must equal the half r squared theta, because if this area here is 1/3 of this area that I've got over here, then 3 times that small area would make it equal to that one. So there's an expression that takes that information and connects the two areas that we are working out. Alright, so now we've just got to go and solve, and we can again factorize the theta out. So I'm going to take theta out the brackets over here, and we'll put that theta just outside the bracket here. Okay, but now because there's theta on both sides, the thetas can cancel. Alright, let's see what else we've got now. We can also say that this is 6r, 3 times the 2r is 6r, and 3 times the 2 is 6, and that must equal a half r squared theta. Well, not theta, just half r squared, because the thetas are already cancelled. So this leaves us with a quadratic expression in r. Okay, I'm going to also multiply everything by 2 just to get rid of that half, and then I'm going to take everything over onto the right hand side, leaving a 0. Okay, so if I multiply by 2, I'll get the following. I'll get r squared, and on this side it'll be 12r and plus 12. And that must equal 0. Okay, so now the question is, can we factorize this so that we can solve for r? Well, the factors of 12 are 12 and 1, 6 and 2, sorry, or 3 and 4. But nothing gives me a nice value for r, so I'm going to have to go to the quadratic formula and say that my r value must equal minus b, which is minus 12, which is 12, plus or minus the square root of b squared, which is 144, minus 4 times a, which is 1, and c, which is 12, so that's 48. And then I'm going to get over 2a, which is just 2. Alright, so we can go and solve this, and we would get 144 minus 48 in the brackets, which is 96. Okay, so 12 plus the root of 96 over 2, so that's basically 12 plus or minus the root of 96 over 2. This is the value for r. So let's go and see what that gives us. So 12 plus 96 root and divided by 2 gives us an answer for 10.89. And if I go 12 minus root 96, I get an answer of 1.1. Alright, so there are two possible answers for the value of r, but we're going to ignore the smaller one for the simple reason that we can see that on the picture r has to be bigger than the 2 centimeters that we had for the previous one, and that would make a diagram that wouldn't be able to be drawn this way. So the one that we're looking for is definitely the 10.89 and not the 1.1. Okay, so there we go. That's number 3. Quite a long question, you can see, and needing all kinds of mathematics to get to the answer. Take note of that example. It's a very important skill that you are using to get that one. We've got one more question to do, and that's going to be this question number 4 over here that I'm going to bring out. So here it comes. Let's just make it a bit bigger so we can see. Right, so this is a multi-part question again. Let's make it slightly bigger. Right, and we've got a arc ADC, which has a center O and a radius r and an angle of 20 radians, sorry, not 20, 2 theta radians at the center. The ABC, they say, is a semicircle, so, and AC therefore is a diameter. We must also show that the length of AC is 2r sine theta. Okay, so this one relies on some trig, which we have not yet done, but maybe we can do it without that trig. So first of all, what I'm going to try without the trig is to do the following. Okay, I'm going to draw a line which is perpendicular to AC, and that would be a height of the triangle. And since this is an isosceles triangle AOC, you can see both sides are r. We know that that line is in the center of the triangle. Alright, and that means it'll also split the angle, which means that each of the angles at the center there are theta. Okay, now that means I could express the sides of the triangle in terms of ratios. Now we know that this height that I've drawn in, if I said that height over r, that would be sine of, sorry, cos of theta, this theta over here, because that's adjacent over here, and the r is the hypotenuse. So I could write that cos theta is equal to the height over r. But that means that the height is equal to r cos theta. Okay? Now, by the same token, this half of the line here, and let's call that A, let's make it E over here. Okay, so AE, that would be if I said that side over the r, I'd have sine theta, and therefore the AE can be expressed as r sine theta if I multiply the r across. Alright, so if that's r sine theta, then the whole of that line, so AE plus EC, because it's the same on the other side, would then just be 2 times r sine theta. So there we've done that without using some of the trick that you're going to learn a little bit later on. Okay, so that's the first thing that we needed to do, was show that AC is 2r sine theta. Okay, so that just happens with normal trig if you use some ratio expressions. So we've shown that. So we're probably going to use that in the next question. So it now says find expressions in terms of r and theta for the areas of sector OA and DC. So OADC is OADC. It's the small sector running over here. Alright. Well, what is area of a sector? Simple formula again. Area is a half r squared theta, but in this case our theta is 2 theta, so the answer is just that it's 2 theta times a half times r squared, but 2 times a half is just 1, so we end up with r squared theta. Okay, so there we go. So that is the expression for OADC. Now I'm going to write this up top here just so we can keep it. We probably need it a little bit later. Now they want the area of the segment ADC. Okay, well, the area of the segment, which is this little bit here, must be made up of the area of the sector minus the area of the triangle. Alright, well, do we know the formula for the area of a triangle? It is a half base times height, and the base we already knew was 2r sine theta. The height was r cos theta. Okay, so let's put those two together. So the area of the triangle, half base height, is a half 2r sine theta times r cos theta. And that comes out as a half times 2r is just r, so it's r squared sine theta cos theta. Okay, r squared sine theta cos theta. Let's put that also up top here. So, sorry, r squared sine theta cos theta. So that's my area of my triangle. Now we've got to subtract the two areas if we're going to find the area of the segment. So the area of the segment must be r squared theta minus r squared sine theta cos theta, and that is r squared theta minus sine theta cos theta. Now, in the back of the book they might have a slightly different answer. I haven't checked yet, and that's because there's something called a trig identity for the sine theta cos theta. Now again, I'm not going to worry too much about that because your answer is correct, but you can write sine theta cos theta as the following: a half sine 2 theta. So they may have had the following as an answer. Okay, if they did have that, just trust me on the identity. We'll get to that in a little bit more time into the future. Okay, so the last little bit of the question now asks for the area of the shaded region that they gave us. So not my shaded region, but the one that they actually gave us over there. And let's just have a look and see what that is now. There is a semicircle, and the semicircle's area would be a half pi r squared. Okay, remember pi r squared is the area of a circle, so a semicircle will be half pi r squared. Now we've already found the segment area, so the shaded region would be the semicircle's area minus that shaded region area that we already found. Okay, so being a half pi r squared, it is a half pi. What is the r? Now the r is the half the length of AC, so that'll just be r sine theta. So that's r squared sine squared theta. Okay, so I squared the r sine theta and got r squared sine squared theta. Okay, but we're going to subtract the area of the segment we found, which is r squared sine theta cos theta. Cos theta. Right. So we could factorize r squared out because that's common to both, and we're left with the half pi, which I'll put at the top here, so pi over 2 sine squared theta minus, and remember we had a half sine 2 theta if we used our identity, which I'm going to use here because I think they'll probably leave it like that. That then is an expression for the shaded region. Alright, so the important thing now is not to get scared when you don't have numbers, but to continue doing the same things and applying the values in carefully. This is really some skilled work at substituting and putting in answers where there aren't numbers, and using letters and factorizing, all skills that you need to be very comfortable with. Okay, that at least gives you a couple of those. You can try some of the others yourself, and let's see how you go from there.